The Tacoma Narrows Bridge tragically collapsed, resulting in the loss of millions of dollars. My team and I have come up with a new innovative design for the bridge to prevent it from ever collapsing again. First, I'll answer the question of why the bridge collapsed. I will explain what happened to the bridge as it was hit by winds at constant high speeds, as it entered torsional flutter, then as it entered vortex shredding. The original bridge was composed of 8-foot plate girders along its whole length. When the wind was to hit these girders, it would be forced around the bridge, causing the bridge to sway side to side, entering torsional flutter. Since plate girders are only intended for short-span bridges, the wind had a significant effect on the long, flexible bridge, ultimately being the reason for its collapse. In 1940, on November 7th, when there were constant high winds, the bridge began to sway, creating a harmonic vibrating motion increasing over time. This is called torsional flutter. The bridge then entered the vortex shredding phase. Wind separated when hitting the bridge, with most wind getting caught underneath the bridge, creating lift. Most of the rest of the wind traveled below the bridge rather than over top, making the wind denser on the bottom, also creating lift. Since the bridge was under such stressful conditions, the steel became more of an elastic structure. Twisting of the deck caused wind flow separation to increase, forming a vortex. This is exactly why plate girders were the wrong choice for this bridge. The optimal choice is to replace these girders with 25-foot trusses, specifically Warren trusses composed of equilateral triangles with each beam supporting an equal amount of force. This is the perfect choice since they evenly distribute loads across the bridge into the towers, which then travel into the ground. This design will work because if constant heavy winds were to act on this bridge, the bridge would not sway like the previous one that was built. Because of the long open trusses, which provide more than enough support for the bridge and heavy loads it will possess, the wind would easily pass through the bridge instead of around the bridge. This will provide minimal forces of wind acting upon the bridge, making the bridge very structurally sound. Again, Warren trusses would be perfect for this bridge since they are able to distribute point loads to a much wider area. As shown, the truss carries tension and compression alternately along the bridge with each beam. It is also impossible for truss members to attract moment or torsion forces upon it, making it an even more effective choice. Trusses also create large open spaces with less material, whereas the use of plate girders become uneconomical as bridges become longer by using much more material. The proposed idea for the new bridge is to keep the bridge as a suspension bridge. This is the perfect type of bridge for this scenario since it can have multiple cables holding the bridge up. The cables would specifically be made of steel, as a 0.1-inch thick cable can support over half a ton without breaking. This makes a suspension bridge an ideal solution for this long bridge. To lower costs, my team and I have decided to reuse functioning parts of the previous bridge and use them on the new bridge. This includes keeping the towers on either end of the land, one on the city of Tacoma and the other on the Kitsap Peninsula. Other materials will also be reused where appropriate, such as cables and scraps of steel, which can be reformed and placed where they will be most effective. The expected deadlines are as shown. We predict that the project will take approximately 3 months to be approved, 7 months to assemble the needed materials, 10 months for the construction of the deck and tower in the Puget Sound, where the bridge passes over, 7 months to attach the cables and pave the bridge, and finally 3 months to run tests on the bridge so it can be open to the public. This comes out to an expected 30 months' time. The cost of the project includes cleanup of the previous bridge, costs of materials, assembly costs, as well as other needs that may be necessary in the construction of the bridge. This comes out to an expected total of $7 million. To summarize, my team and I have identified the problem with the previous bridge design and have designed an alternative technique of adding trusses to the bridge to ensure minimal wind resistance. While lowering costs, this is a structurally sound design that will prove to be very effective while lasting for decades to come.